You know, everything moves. But how do we actually talk about it? I mean, how do we speak the language of motion? Well, today we're diving into kinematics, the science that gives us the exact words and really the rules to describe how anything from a car to a planet gets from one place to another.
Think about it. From just walking down the street to the incredible, overwhelming power of a rocket lifting off the launch pad, motion it's a fundamental part of our world. We see it everywhere, every single day.
So right, how do scientists and engineers go from just looking at something moving to being able to precisely describe it, predict where it's going to go, and even control it? Well, the answer lies in a branch of physics called kinematics, and trust me, it's more straightforward than you might think.
Okay, first up, what even is kinematics? At its heart, it's really all about the geometry of movement. Now, this is the most important thing to get right off the bat. Kinematics is all about the what and the how of motion, but it completely ignores the why. So we're describing an object's path, we're describing its speed, but we're not getting into the forces, like a push or gravity, that are actually causing that motion. We'll save that for later.
And here's the cool part. To describe almost any motion you can think of, we really only need three main ideas. Think of them as our fundamental building blocks: position, velocity, and acceleration.
So let's start with the absolute basics, the most basic question you can ask. Where is it? That sounds super simple, right? But in physics, being precise is everything.
So we have position, which we usually label with the letter S. And it's not just a number, it's not just a distance, it's how far you are from a specific starting point. We call that the origin, and, crucially, in what direction. Like, we might say movement to the right is positive, and movement to the left is negative.
And that brings us to a super related idea called displacement. Now, this is not the total distance you walked. It's just the straight line distance from where you started to where you ended. It's like the ultimate shortcut, completely ignoring whatever scenic route you might have taken.
Here's a perfect example to really nail this down. Imagine you walk one full lap around a 400-meter track. You end up right back where you started, yeah? Well, the total distance you traveled is 400 meters, but your displacement is 0, because you didn't end up anywhere different from where you began.
Okay, this leads us perfectly into our next big concept. And honestly, this is one that trips a lot of people up. So let's talk about the difference between velocity and speed.
The difference is actually pretty simple, but it is so important. Speed is just a number. It's how fast you're going. That's it. Velocity, on the other hand, is your speed plus your direction. So if a car is going 60 miles an hour, that's its speed. But if a car is going 60 miles an hour due north, now we're talking about its velocity.
Yeah, one of the sources we looked at just nails this distinction. Let's go back to our track example for a sec. You ran that 400-meter lap, right? Your average speed was definitely something. I mean, you were moving. But because your final displacement was 0, your average velocity for that whole lap was also 0. See how much that direction matters? It's kind of wild.
All right, so we've got position, that's where something is. We've got velocity, that's how fast and in what direction it's going. But what about when that velocity changes? Well, that brings us to our third and final core concept, acceleration.
So acceleration is any change in velocity, and I mean any change. Speeding up, that's acceleration. Slowing down, yep, that's also acceleration. Sometimes people call it deceleration, but in physics, it's all acceleration. And here's the kicker, just changing your direction, even if your speed stays exactly the same, is also an acceleration.
Okay, time for a classic physics brain teaser. I want you to really think about this for a second. Is it possible for an object to have 0 velocity, to be completely still for just an instant, but still be accelerating?
Well, to figure this out, just picture this. You toss a ball straight up into the air. What happens right at the very, very top of its path? For just a tiny split second, it hangs there. It seems totally motionless.
And the answer is absolutely yes. At that single instant at the peak, the ball's velocity is 0. But is gravity gone? No way. Gravity is still pulling it down. And it's that constant pull that's actively changing its velocity from going up to going down. That change is acceleration, and it's happening the entire time, even at that moment of stillness.
Okay, so let's recap. We've got our three essential tools: position, velocity, and acceleration. Now for the really fun part. Let's see how we can put them all together to solve some actual, real-world problems.
So, when an object has a constant acceleration, and this happens a lot in these kinds of problems, we get these three beautiful, powerful equations. Now, don't let the math scare you. Just think of these as recipes for predicting motion. If you know a few of the ingredients, like time or initial speed, these formulas let you figure out the rest.
Let's try one out. Here's a great problem from one of our sources. Picture this. A rocket is already flying upwards at 75 meters per second. But then when it's 40 meters up, the engine suddenly fails. Uh-oh. So the question is, how much higher will it coast before it starts falling back down?
Okay, so how do we tackle this? We just follow a simple, logical process. Step 1, we write down everything we know. We know its starting speed, its starting height, and we know the acceleration. That's just gravity pulling it down. Step 2, we define what we're looking for. We want the maximum height. And the light bulb moment here is realizing that at its peak, its velocity will be 0 for an instant. Step 3, we look at our 3 recipe equations and pick the one that connects all the things we know with the one thing we want to know, the final height. And finally, step 4, we just plug in the numbers and solve.
And boom, just like that, the math gives us the answer. The rocket will keep going up until it reaches a height of 327 meters. That's it. That's the incredible predictive power of kinematics.
And that's really the beauty of this whole thing, isn't it? The exact same rules, the same handful of equations that describe our failing rocket also describe a car braking at a stoplight or a boat cruising across a lake. It's the universal language for all motion in a straight line.
So we've pretty much cracked the code for motion in a straight line. But, the real world isn't always straight lines, is it? What happens when the path starts to curve? Think about a planet orbiting the sun, or even just a car taking a corner. What then? Well, that adds a whole new layer to this language of motion. But that, my friends, is a story for another day.